Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about repeated games. My name is Rick, and my co-teacher, who originally prepared these notes, is Christoph. Let me break down an outline of what we want to cover today. As we've looked at a few times in the past already, we're going to continue looking at the problem of cooperation. And we'll look at whether repeated games can help solve the problem. The way we'll do that is by introducing a concept called memory 1 strategies. And we'll look at some solutions for these strategies, meaning we're going to develop some solution concepts. Then we'll explore the danger of short-term rationality and look at some ways to get around that. One of them being long-term rationality, and the other being something we'll call the shadow of the future. Okay, so let's start with the problem of cooperation. And as we've discussed before, the problem is how do you maintain beneficial cooperation when there's a temptation to defect? So we've looked at that recently in light of the public goods game. Today we're going to go back to a simpler case. The public goods game was a multiplayer game, a many-player game. We're going to go back to a two-player game. So a good example where there is this problem of cooperation in a two-player game is the prisoner's dilemma. And the basic idea there is that each player has to pay a cost C in order to give a benefit B to the other player. So the payoff matrix looks like, well, what does it look like? If the other player gives me a benefit, then if the other player is cooperating, I get a benefit B. If I have to pay a cost when I cooperate, then I have to pay a cost here and here. And if nobody is cooperating, we're all defecting, then there is no benefit and no cost. So in this case, we're going to assume that the benefit is worthwhile. So B is bigger than C and C is bigger than 0. Okay, and as you can see, D dominates in this game. So rationally, it's always better to defect. So players will choose defection, rational players will, even though they would both prefer to mutually cooperate. And that gets the essence of the problem of cooperation. They can't maintain that cooperation because of that temptation to shift to defection. So what would this look like in a repeated game? Let's say we play M rounds. Well, now it's not so simple as just choosing C or D, because what you might choose might depend on what's happened in the past or what you anticipate coming up in the future. So it's not as easy as it was before. So how do we address this? One approach is to look at a specific set of strategies that we'll call memory 1 strategies. So to introduce that, let me back up a little bit. The idea is that in each round, the player has to choose either to cooperate or defect, which are, let's call those the short-term strategies. Those are the things I have to choose to do right now. So deciding what to do, which short-term strategy to choose, that might depend on what's come before. So what we could do is create some things, let's call them long-term strategies, which can be conditional in the sense that they can depend on what's happened in the past. So they can be conditional responses. As I said, they can be conditional responses to past interactions. And in principle, they can depend on everything that's come before, and that's a little tricky to handle. So instead, let's look at a simpler case. These memory 1 strategies only depend on what happened in the prior round. So they remember one round back. That's where the term memory 1 comes from. So this term, you'll probably see it some more in the class, so you should get used to it. Let's look at some examples of memory 1 strategies. So there is one we could call all D, which would just be always choose D, defect. Or the converse of that would be all C, always choose cooperate. There's another one that you may have heard of before. It's pretty famous, and we can talk about why a little bit later. It's called tit for tat. I don't know the historical origins of this. I think it comes from this for that, so get your mind out of the gutter. And the idea is that you start by cooperating, and in every subsequent round, you just do what the other player did in the last round. Another one that comes up sometimes, and you might see it sometimes, we'll call it Grim. Again, it starts with cooperate, and then keep playing C every round until the other player defects, just once. And once they do defect, then a Grim player will play D for the whole rest of the game. So you really don't want to get on their bad side. And another one that's interesting to look at is called Pavlov. And you might think of it as win, stay, lose, shift. Again, what happens is they start by playing C, and in subsequent rounds, if the outcome was good, meaning that it's one of the top two payoffs, which would be B or B minus C, then you keep doing what you were doing. And if it wasn't good, if you got one of the lower two payoffs, that would be 0 or minus C, then you shift. Maybe I should say that different. Then you switch strategies. Let's say the opposite strategy. And those are just 5 examples of strategies, long-term strategies or memory one strategies that people have studied. But that's not an exhaustive list. There are many more. So what's the point of using these memory one strategies? Well, one of the points is that they're easy to encode or codify, and so it makes them easy to work with. And the way you do that is you write down what the choice would be in the first round, and then given each of the 4 possible outcomes in later rounds, in each round, you say what the response would be. What would you play in the next round if this was the outcome in the prior round? So there will be 4 things you need to specify then. So for example, we could write down the strategies that we've written already. They were all D, all C, tit for tat, Grimm, and Pavlov. And then we could say what the response would be in the first round. And those are pretty easy to write down. For all D, well, they're going to defect in the first round. All C cooperates. And all the other strategies that we mentioned, they start with C. There, and here. So those are all C's. And the next thing we need to write down is the response conditioned on the prior round. So let's write it like this. What we'll put here is my choice last round, and here we'll put what your choice was in the last round. And what can those be? It could be that we both cooperated in the last round, or maybe I cooperated and you defected, or maybe I defected and you cooperated, or we both defected. And now I just need to write down what the choice would be in each of these strategies, given these pairs of strategies being played in the last round. So if we both cooperated in the last round, then all D would say defect. I don't know how that would have occurred, because it should never be that I cooperated in the last round, so this doesn't even really make too much sense, but certainly we know that all D would choose defect no matter what. So we can write out the full set of choices for all D just like that. No matter what happened in the last round, I will choose to defect. And likewise, it's easy for all C. They just always cooperate, no matter what happened. Let's look at tit for tat. So the idea there is they start with C, we got that already, then they copy the other player's prior choice. So they just do exactly, I, as a tit for tat player, will do what you did in the last round. This column or this row right here says what you did in the last round, so I will copy exactly that. If you cooperated last time, I'll cooperate this time. If you defected, I'll defect. If you cooperated, I'll cooperate. And defect gets defect. Okay, now let's look at Grimm. So Grimm says, keep playing cooperate until the other player plays D once. Then play D for the rest of the game. So how do we encode that? So some things are easy about this. If you defect in a round, then the next round I will defect. So that's here and here. The trick now is, what do I put in for these other two? Well, what should change me to start defecting? Only if you defected in the past. And if you defected in the past, I will switch to D. And so if I'm a D, that means that's an indicator that at some point in the past, you must have defected. And so I should keep defecting. Likewise, if I'm currently cooperating, that means you must never have defected in the past. And if you don't defect this time, you still cooperate, then I should keep cooperating. Okay, so that's Grimm written as a memory one strategy. What about Pavlov? Pavlov says, I should start with cooperating, got that. If I get one of the higher payoffs, B or B minus C, then keep doing what I did. And if I get one of the lower payoffs, then switch my strategy. Okay, so when will I get one of the higher payoffs? If we both cooperate, I will get B minus C, so that is one of the higher payoffs. So I should continue to play C. If I defect and you cooperate, then I get the benefit without paying the cost, so I get B. That's the higher payoff. I should continue to do what I'm doing, which is playing D. What if I play C and you play D? Then I'm going to get the worst payoff, minus C. I have to pay the cost and I get no benefit. In that case, I should rethink what I'm doing and switch my strategy. I'll switch to D. And what if we both play defect? Then nobody gets anything. That's one of the two low strategies, low payoffs. So I should switch. So I will switch to cooperate. Okay, so those are the various strategies expressed as memory one I should say pure memory one strategies, but let's not get into that at this point. We can talk about it another time. They are not a complete set of all strategies of this type. If I just wanted to write down a string of 5 letters that are either D's or C's, I could write down a bunch more. In fact, I could put a D or a C in each one of those 5 spots, and that means there would be 2 to the power of 5 possible combinations I could write, which is 32. So there are 32, let's call them pure memory 1 strategies. Okay, so for today's lecture, we're going to look at one particular pair of strategies for the remainder of this lecture, and that will be tit for tat versus all D. And we're going to look at these two because all D we know is a defecting strategy, so it's going to pull us away from competition. Tit for tat could promote cooperation, but we don't know. What we do know from historical studies is that it's a very successful strategy. And we might talk about this in the classroom a little bit more. So let's imagine we have 2 options. We can play tit for tat, or we can play all D. How would a game develop in the long term if these were the 2 options? To look at that, we need to work out what the payoff is in each round when these strategies play against each other and themselves, and work out the total payoff over the long term. So let's imagine, first of all, that we have tit for tat versus all D. So if we had players that were playing, one of them was playing tit for tat and the other one was playing all D, what would happen? We can look at this by considering what happens in each round. So we would start by looking at the first round, second round, and eventually get up to the nth round. And let's look at that. So as a reminder, I'll just put up in the corner here the payoffs in each round. So those strategies available in each round, the short-term strategies are to play C or D, and the payoffs are B minus C, B minus C, and 0. So in the first round, what happens? Tit for tat plays cooperate, all D plays defect. So it's C versus D. The player who plays C gets minus C for their payoff in that round, and that's tit for tat. And the player who plays D gets B for their payoff, and that's all D. So tit for tat gets a payoff of minus C, and all D gets a payoff of B. And what about the second round? What does tit for tat do? It does whatever the other player did in the last round. So it just looks back at the first round and says, what did the other player do? They played D. So I will play D this time. What does all D do? Well, pretty obviously, they play all D. So in this round, we're playing D versus D. Everybody gets 0. And I think you can see where this is going. All D always plays D. So tit for tat will adopt that and also always play D from now on. So once we get to the nth round, they're still going to be playing D and earning 0 and 0. And if we just total that up to figure out what they get over all the rounds, then they get 0 over most of the rounds. The only payoff they get is from the first round, and tit for tat gets a score of minus C, all D gets a score of plus B, and there we have it. That's the payoff for tit for tat versus all D. So what we want to do is look at these 2 different strategies and figure out what the payoff is for each one of them, not just against each other, but also against themselves, because we want to build up a long-term payoff matrix for the long game, you might say. So what if instead of tit for tat versus all D, we were looking at tit for tat versus itself? In that case, they would cooperate in the first round, which means they would get B minus C each, and they would keep doing that in every round because they would just look back at the previous round and see that the other player cooperated in the last round, so they'll cooperate in this round. So if we want to add it up, it's just M rounds of getting B minus C in each round. So they will get M times B minus C. And that's the same for either one of them. What about all D against itself? I think this is an easy one to work out. They're going to play D in the first round, and since they're both playing D, they're going to get 0 payoff, and they will keep doing that. So they will get a total of 0 after playing M rounds. So we can use this to build up a payoff matrix for the long game. The 2 strategies are tit for tat and all D. And we see here that when tit for tat plays itself in a long game, then they will get a total of M times B minus C. When all D plays against itself, it will get 0. And when they play each other, tit for tat will get minus C, and all D will get plus B. So there we have the payoff matrix if they play M rounds against each other, choosing one of these 2 strategies. So you'll notice this is still a symmetric game. They can take on either role. either the row player or the column player. So we've looked at all sorts of symmetric games, and we found that there are generally 4 types. There was Prisoner's Dilemma, Harmony, Snowdrift, and Stag Hunt. And so the question is, which one is this? And you'll see that which outcome is preferred will somehow seems to depend on M, the number of rounds. So there are 2 possible cases. First of all, if M is small, and what we mean by that, you can work out for yourself. It means M is smaller than B divided by B minus C. That's one of the cases. The other case is if M is big, which means it's bigger than B over B minus C. And why does that matter? Because we need to compare M times B minus C versus B to determine whether the preference arrow points up or down. And that will determine what kind of game we're looking at. On the right-hand side here, things are pretty easy. We can see that since C is bigger than 0, then negative C is smaller than 0, so the preference arrow points down. Let's start filling this in. I'm going to draw the preference arrows for these 2 cases. So on the right, we already realized that the preference arrow points down. On the left, if M is small, then this payoff in the top is smaller than this payoff, so the preference arrow points down, which means we have a game of Prisoner's Dilemma going on. But if M is big, then this top row is bigger than the bottom row, and the arrow turns around and points up, which, if you remember, is Stag Hunt. So that's kind of neat, I think. What we've done here is turn a game of the Prisoner's Dilemma in 1 round into possibly a Stag Hunt game if we repeat it over enough rounds. And we give the players the options of playing tit for tat or just defecting. And we've already looked at Stag Hunt a fair bit, so we know a fair bit about it. But let's review some of that. Let's look at the solution concepts when under the, let's say, the evolutionary case. So if we let X be the frequency of tit-for-tatters in the population, then I'm not going to go through the derivation again, but we've done this, and we know what things look like. In Stag Hunt, there's an unstable equilibrium in the middle at some X star, and there are stable equilibria at the endpoints at X equals 0 and 1. So if we play a repeated game with enough rounds in a population that consists of tit for tat or all D, we will see that the game turns into Stag Hunt, and because of that, there is a possibility of maintaining cooperation. All we need is that the starting population has enough tit for tatters in it from the very beginning. I won't bother working out what X star is at this point because I also want to go through the economic solution, and I will figure out what P star Q star are for the mixed Nash equilibrium. And as you already know, that's the same as X star. So looking at the economic solution concepts, the most important one is the Nash equilibrium. And Stag Hunt, as we know, has 3 Nash equilibria. Those are both play tit for tat, so that's one of the pure ones, and both playing all D, that's the other one. And there's the mixed Nash equilibrium. So which one are they actually going to prefer? Which one should rational agents prefer? To figure that out, we need to know which one pays off the most. So let's figure out what the expected utility is for each one of these. If both players play tit for tat, they will get M times B minus C. That is their expected utility. If they both play all D, then we already know they will get 0. So that's their expected utility. What about the mixed Nash equilibrium? Well, okay, that's going to take a little bit more work to figure out. But let's go through the exercise. It's useful. First, we need to figure out where the mixed Nash equilibrium is. And to do that, we find the Q star that makes the row player indifferent. We could do it the other way around. P star that makes the column player indifferent. It's a symmetric game, so it doesn't matter. So the payoff for the row player, if they want to play tit for tat, and they know the other player is playing Q star. Well, it's M times B minus C times Q star. That's just this box here. And if we know the column player is playing Q star, so that's probability Q star of playing this, of getting this, or 1 minus Q star chance of getting this. So we have to add this on to get the expected utility. So there's a minus C, which happens with a probability of 1 minus Q star. So that's the expected utility for playing the top row. The row player is going to be indifferent, so that should be the same as the expected utility of playing the bottom row. And in the bottom row, they either get B with a chance Q star or 0 with a chance of 1 minus q star. So of course that's just b times q star. So from that, the indifference condition is the expected utility for playing the top row becomes equal to the expected utility of playing the bottom row, which if we do the math for that, we will find, and you should try this and make sure it makes sense to you, that q star equals c times, or divided by m minus 1 times b minus c. And of course, that's also equal to p star. And that's just because we're looking at a symmetric game. Okay, why did we need that? We needed it to compare the expected utilities for all three Nash equilibria. And we can do that now. So the expected utility, let me say it differently. Let me back up and say this a little bit differently. So what I want to really do is decide which the players would prefer. And if I just want to compare expected utility of the tit-for-tat Nash equilibrium, that's m times b minus c, versus all d, I can see that the tit-for-tat Nash equilibrium is preferred over all d. What about the mixed Nash equilibrium? Well, we can figure out what that expected utility is, because we already know that each player has been made indifferent, and so their expected utilities are given right here. And in particular, we can choose either of these, and in particular, this is a nice easy form to use. So we could say the expected utility at the mixed Nash equilibrium is b times q star. And we know what q star is, because it's right up here. So plugging that in, we get b times c divided by m minus 1 times b minus c. And now we can compare that to the other payoffs at the other Nash equilibria. Maybe we don't know exactly what the expected utility of the mixed Nash equilibrium is, but just this form right here already tells us a lot, because q star is bigger than 0, because we know we're playing stag hunt, so there's an interior equilibrium, and b is bigger than 0. So that means that the expected utility of the mixed Nash equilibrium is bigger than 0. Which is the expected utility of the all D Nash equilibrium. So all D is never preferred. The two other Nash equilibria are better. And the next question then, of course, is comparing the remaining two Nash equilibria. So that was the tit-for-tat versus the mixed Nash equilibria. And to figure this out, we're going to use a little bit of a trick. Just recall the definition, or the requirement we had for getting stag hunt at all. And that was that m is bigger than b over b minus c. That's right here. This is what we needed for stag hunt to occur in the first place. So if that's true, that tells us something about how big m minus 1 has to be, because m minus 1 has to be bigger than, first of all, b divided by b minus c minus 1, but 1 can be written as b minus c divided by b minus c. So all of this stuff on the right can just be written as c divided by b minus c. You can check that for yourself. And that means that m times m minus 1 is bigger than the two things that each one is bigger than multiplied together. So m is bigger than that, and m minus 1 is bigger than that. So m times m minus 1 must be bigger than those two things multiplied together. And those things multiplied together, let me just write it as b times c divided by b minus c squared. Just to keep you on track here, we're putting together an argument to figure out which expected utility is bigger for which Nash equilibrium. We can reorganize that. We can multiply both sides by b minus c and divide both by m minus 1, and we will see that it's m times b minus c is bigger than bc over m minus 1 b minus c. What's the big deal with that? Well, the expected utility of the mixed Nash equilibrium is this, which is everything on the right-hand side of the inequality, and the expected utility of the tit-for-tat Nash equilibrium is everything on the left-hand side. So what we've really just discovered is that the expected utility of the tit-for-tat Nash equilibrium is more than the expected utility of the mixed Nash equilibrium. And that means that of the three Nash equilibria, the option of playing pure tit-for-tat, both players playing that, is the preferred Nash equilibrium for both players in the long-term game. In other words, both players would prefer to play tit-for-tat so that they arrive at that Nash equilibrium. And remember that if they're both playing tit-for-tat, that means they're always playing C in the short game, so we've just saved cooperation. If there are enough rounds and the players have the option of playing tit-for-tat or all D, they will play tit-for-tat and they will cooperate in every round. That sounds good, right? There's just one detail that we need to be aware of that could break all of this down, and that is the danger of short-term rationality. So what do I mean by that? Let's go through it. We've already established that there are M rounds, so these players could play these strategies that we've talked about, but what should they do in the last round? In the last round, there's a bit of a problem because there's no incentive to cooperate anymore, because they're not going to see each other anymore. It's effectively a one-shot interaction. So if we were thinking about the two options of playing tit for tat or all D, what if we made a little bit more of a sophisticated version of tit for tat? Let's call it tit for tat prime. And what they do is they play tit for tat, but they defect in the last round. So what would that game look like if we just had the possibility of tit for tat and the new tit for tat prime strategies? So the only thing that changes is the last round. So over the first M-1 rounds, they'll play mutual cooperation, and then in the last round, things could change. If we just look at tit for tat against itself, then things don't change. It's still just B minus C. What if we looked at the other case, tit for tat prime against itself? Same thing at first, M-1 rounds of getting B minus C, but in the last round, they defect against each other, so they get 0. And what if the two strategies play against each other? Again, in the first M-1 rounds, everything's the same, but tit for tat prime in the last round defects, and tit for tat still cooperates, so tit for tat prime gets B, whereas tit for tat pays a cost C. And you'll see everything is the same at first, and it's only the last round that changes things, but it changes it in a very important way, because now our preference arrows point down and the long game becomes a prisoner's dilemma, and we see that our new strategy, tit for tat prime, dominates. So now we've got a strategy that's very much like tit for tat, but it's a little bit better. So we should all play that, right? If everybody plays that, we know what's going to happen in the last round. What should we do in the second last round? If we know what everybody's going to do in the last round, they're going to defect, then what's our incentive to cooperate in the second last round? We don't have any. And I hope you can see we've kind of come back full circle. And instead of thinking about what we should do in the very last round, now we're looking at the second last round, and we see that if we know what the other player is going to do in the very last round, then we should defect in the second last round. So we could introduce a more sophisticated version of TFT prime. Maybe we could call it TFT prime, double prime. And they do the same thing as TFT prime, except they defect in the second last round and the last round. If we look at the long game payoff matrix, we'll see that TFT prime, double prime, dominates. And again, we have a prisoner's dilemma, and it's better to play TFT double prime. And given that, wouldn't it be better to play TFT triple prime, defecting in all the last 3 rounds? Yes, it would. And so on and so forth. That reasoning will take us all the way back to playing all D. What we've done here is we've created an argument based on short-term rationality, looking out for what's best for us in a single round instead of trying to optimize and make the best of the whole game. And that has led us to choosing all D over tit for tat. And you may recognize this. It's another form of backwards inductions, which is the technique we used in extensive form games to figure out the subgame perfect equilibrium. But if we think long term, then we know the players prefer tit for tat over all D. So there's this kind of dichotomy. By looking at short term, what's rational in the short term, we can arrive at outcomes that are not the rational solution in the long term. Another way to think about that is that it can be rational in the long term to forego short-term gains. That kind of thinking requires you always to be looking at the long term and to give up looking at the short term and what's in your best interest in the short term. And that can be, well, in some cases that might not make sense. So is there another way to sustain cooperation without requiring this kind of long view? Yeah, the other way is this idea of the shadow of the future, which sounds kind of ominous. So if players are rational in the short term, how can we get away from this circular argument that breaks down cooperation? Well, one way is if we can get rid of the certainty of the end of the game. The problem with having M rounds in particular was that all the players know when the game is going to end, and so they can change their behavior in the last round, and therefore the second last round, and therefore the third last round, and so on. But if they don't know when that game is going to end, then they can't take that step. So if we make the end of game unknown, for example, we could play another round with some probability, then the players can't make that switch in their behavior. The players will never know if the current round is the last round. And that's the idea behind this term, shadow of the future. The possibility of future retaliation helps to maintain cooperation. So we've seen here a couple ways we can maintain cooperation. One is to restrict your thinking to your long-term utility. But that's a little bit of a weird thing because you're giving up opportunities for short-term gains for the long term. And the alternative is if the structure of the game is changed so that you don't know when it ends, then it makes it easier to maintain cooperation. Okay, so that's the gist of it. Let's just review what we covered today. First of all, we looked at the problem of cooperation. And we explored the idea that maybe repeated games could help maintain it. To study repeated games, we introduced a concept of memory one strategies. We looked at a particular pair of memory one strategies, and that was tit for tat versus all D. We applied our solution concepts, and we saw that repeating a game can help save cooperation, at least in the specific case of these two strategies we looked at. But even there was still the danger of short-term rationality. And we looked at two ways of getting around that problem. The first one was to actually give up opportunities to maximize long-term utility. And the second was actually changing the nature of this game so it wasn't clear when it ended. And that was the idea behind the shadow of the future. Okay, that's all for today. Thanks for watching.